Okay, so in this section, we will talk about the row reduction and the echelon form. So in the previous section, we talked about what is a system of linear equations. And on top of that, we talked about what is the matrix and what is the augmented matrix. We conducted some row operation for the augmented matrix, right? So this section, actually, it's an improvement for the method we used in the previous section here. And what we call it's called as a row reduction. So, and the method was also called the Gaussian elimination. Okay, but actually, a similar elimination method for the linear system was used by a Chinese mathematician about 250 BC. Okay, that's way earlier than when Gaussian discovered this method. Okay, but commonly people call it Gaussian elimination. Okay, and also this row reduction algorithm, it applies to any matrix. So this row to apply to any matrix. Okay. Doesn't matter if it's augmented matrix or not. Okay, doesn't matter. Okay, and then the first part is let's look at if we have any matrix, and then we want to do something to build it into a triangular matrix. Okay, and also we have a name for that part. Okay, so the first one, starting from the definition, is what we call a matrix is called in an echelon form. Okay, if it has the following properties. So number one is all non-zero rows are above any rows of all zeros. Okay, so in other words, the echelon form of a matrix, that means if you have a row of all zeros, it's definitely going to be at the very bottom. Okay. Number two, each leading entry of a row is in a column to the right of leading entry of the row above it. Okay. Okay. So basically, you're gonna have something like a upper triangular shape. Okay. So let me write those properties down first, and then I will give you some example. So all entries in a column below a leading entry are all zeros. Okay, all zeros. Okay, so echelon forms. What does that mean? Well, let's see. For example, if this is I don't know, 1, 2, 3, 4, 0, 2, 5, 9, and then 0, 0, 3, 14. So this actually matrix is in the echelon form. First of all non-zero rows are above of any rows of all zeros. Okay, we don't have the rows of all zeros. Second, each leading entry of a row is in a column to the right of the leading entry of the row above it. So you can see that this is what we call a leading entry because all the previous part is all zero. It is in a column to the right of the leading entry to the row above it. Do you see that? Right. And then all entries in a column below a leading entry are all zero. So this is the leading entry, right? Because this is the leading entry for the first row, and then correspondingly for the first column. So below are all zeros. This is the leading entry for this column here, and then as you can see that all the entries below here, it is the 0 here. Okay, so this for sure, this is the echelon form. And on top of that, we can reintroduce what we call the reduced echelon form. Okay, which you just need two more properties. The first one is leading entry in each non-zero row is 1. Okay, and then 2 is each leading one is the only non-zero entry in its column. Okay, so those are the two. So leading entry in each non-zero row is 1, and then each leading one is the only non-zero entry in its column. What does that mean? Well, it means something like this. Okay, so those astronauts stands for the some real numbers. Okay, it's arbitrary numbers. So as you can see, that leading entry in each non-zero row is 1, 1, and 1. And each leading one is the only non-zero in its column, right? Others are 0, or 0, 0. Okay, so that's what we call the reduced echelon form. So why we introduce this? Okay, why we introduce this? Well, it's because we have some very important conclusion get involved with those. Okay, the first conclusion here, or the theorem, is each matrix is row equivalent to 1 and only 1 reduced echelon form. Okay, what does that mean? That means when you do the row operations, the echelon form, you might have more than one. Okay, you might have different ones. But if you continue to do the row operation, and then to the very end, you'll find the reduced echelon form, that form is actually, it is unique. In other words, when you start with a matrix and then you perform some row operations, and depending on the order of your operation, and you might come into a very different echelon form. But if you continue to do this operation and trying to reduce into a reduced echelon form, that form, it is unique. Okay, so very important. And on top of that, based on this reduced echelon form, we've also introduced another concept. It's called the pivot position. So pivot position in a matrix A is a location that in this matrix A, that corresponds to a leading one in the reduced echelon form of A, of A. And then a pivot column is a column contains a pivot position. Pivot position. So back to the previous example here. Remember, so this is going to be a pivot position. Corresponding, this is the pivot column. Pivot position, pivot column, pivot position, pivot column. Okay? So, okay. Cool. So, once you get the reduced echelon form, and then it's very easy to find the solution of that linear system. Okay, so in the next video I will talk about one example. Okay, so thank you for watching.